You know, there have been a lot of Morse codes of weather, right? Over 50, 60, 70?
Almost at 100 now.
My goodness, where have I been, right?
Wow.
But of all the topics, this is probably one of my favorites because as a meteorologist, you deal with it every day.
Yeah.
Thickness.
Thickness.
It's a good one for meteorologists to know more about. And those that aren't meteorologists, which is why Jacob's here.
We'll explain it to
Yeah.
you. This is how we diagnose our atmosphere. Like Kevin mentioned, every day we usually take a top-down approach to see what's going on globally and break that down into a more localized forecast. But thickness of layers of our atmosphere, it's defined as the distance between any two constant pressure surfaces. So we're talking about pressure in our atmosphere. The variable or the unit of measure is millibars that meteorologists use. It's a measure of atmospheric pressure. At sea level, the standard air pressure is about 1,013 millibars. And meteorologists usually compare the 1,000 millibar constant pressure surface, which is right around ground level, to the 500 millibar constant pressure surface, which is typically around 18,000 feet above our head, so about halfway up to where planes fly at cruising altitude. So when we compare this 1,000 to 500 millibar pressure surface, we can figure out where cold air masses versus warm air masses are based on the distance between those constant pressure surfaces. In cold air, the thickness is going to be small between those two pressure surfaces versus with warm air, the thickness is a lot larger. That's because of the density of air. With cold air, the molecules are a lot more closely packed together, whereas with warm air, the molecules are more widely spaced apart. They're moving around a lot faster, so the air is less dense with warm air. Therefore, it takes up more space. The thickness is larger with warm air compared to the thickness being smaller. Everything's squeezed down a little bit more with that cold air in place. And we measure this in meters, and it's in thousands of meters usually. And the 1,000 millibar surface will often be below ground or sea level, with the 1,000 to 500 millibar thickness values, taking that into consideration just based on the elevation of Earth's surface. But a couple of ones that meteorologists need to look at. The last zero is often dropped. So if we're taking the difference in height here between 1,000 millibars and 500 millibars, and it's about 5,700 meters, we just chop off that last zero. We call it a 570 thickness value. That thickness, when it's greater than 570, it's associated with tropical air masses. Again, larger thickness, warmer air. 510 thickness with value less than that, that's associated with Arctic air. Again, the thickness is smaller of our atmosphere. The air is more tightly packed together, denser, colder air. 540, so that's 5,400 meters, that distance between the 1,000 and 500 millibar levels. That generally divides the polar air from the mid-latitude air. It's a guide for our rain-snow line, so it can really help to diagnose precipitation types. And all of these thickness levels, again, really help us to figure out where these different types of air masses are, especially diagnosing where tropical versus polar air is. Let's take an example from December 9th of 2019. This is the 1,000 to 500 millibar thickness plotted. And this is the 570 line here, indicating where the tropical air is, well down to the south. The 510 thickness line, well up to our north. And then the 540 line right here, indicating where we kind of have the clashing of air masses. And that was when we had a cold day around here, compared to today, where that 540 line, 5,400 meters, is the thickness between the 1,000 millibar and 500 millibar constant pressure surfaces. That's kind of to our north and east, indicating some milder air coming up into our area. The polar air is much farther up to our north and east with that 510 thickness line. And we can usually diagnose where advection is, or where warm air is moving into a region or cold air is moving into a region, just based on these thickness lines that we're looking at between 1,000 and 500 millibars. And with that 540 line, this blue line on this map here, that can really help us to diagnose where rain is versus snow, just based on how thick the atmosphere is between those two constant pressure surfaces. And it can roughly equate to this map that we show a lot of times on air, with our milder air indicated by the warmer colors and the cooler air indicated by the cooler colors. Again, this is that smaller thickness in our atmosphere, indicating a little bit of a cool down for the end of this week before we get back into that milder air, with our jet stream moving up to the north, but again, it's the thickness here that really plays into those larger scale temperature patterns. And when you have the greater thickness in the atmosphere between 1,000 millibars and 500 millibars, that indicates warmer temperatures. Other ways it's helpful with fronts. Thickness is directly related to the density of the air, as we've talked about, and therefore temperature. Fronts are boundaries between air masses, with air temperature usually decreasing behind a cold front. So behind a cold front, we usually see packed thickness lines. The thickness lines are really close together here, indicating that our temperatures are dropping off rapidly and decreasing behind that cold front. An example here on a large scale, this is just as a general example case. Here's our thickness values plotted. The blue lines here indicate where that colder air is, but below 540 for a thickness value. And then I'm plotting the surface weather on here, and you can see where those fronts are generally lining up to where those thickness lines are closely packed together, and you can kind of see where the cold air is diving south there behind that cold front. Another way it's helpful is with the rain-snow line. We talked about that earlier. The 5,400 meter thickness line closely follows where our surface freezing temperature is, so the rain to the south and east versus snow to the northwest. Another one that's maybe not as well known is the gustiness of our wind. So wind speed is based on the pressure differences at Earth's surface. And we talk about that with a tight pressure gradient indicating higher wind speeds, but the gustiness of those winds can be correlated to thickness. The thickness lines that cross the isobars, which are our constant pressure lines, at right angles indicate the gustiest winds. We have an example here. I'm going to enlarge this here. Wind speeds are similar at both of these points here. Our black lines here are those constant pressure lines, equal pressure isobars, whereas we have our thickness lines here, the dashed lines. And when they're crossing those at right angles, this gets a little complicated here, but basically the winds would be gustier at point number 1 compared to point number 2 because the thickness lines are crossing those isobars at right angles. So another use of those thickness plots that meteorologists have, but as an overall rule, we use them every day for diagnosing where the bigger air masses and temperature differences are across the country and across the globe.
And today, thickness value, I'm guessing is about 545.
That's what it looked like
somewhere.
on that
Yeah,
map,
I mean,
yeah.
so that's a good thing. Above the 540, as meteorologists, we're like, okay, things are looking pretty good.
Milder.
Mild pattern continues. Great job, Jacob. Thank you very much.
You're welcome.
All right.